Okay, so maybe let us get back. I think majority of you have submitted. Okay, so let us get back to options. Check. Okay, so let's continue. So before the break, like we talked about the idea of options, like so which are like one way to define temporally extended actions. Like so in the case of options, each option is a triple. Like you have a set of states from where the option can be enabled, and a policy pi to follow within that option, and like a beta term, like or beta term, like which tells the probability of termination in a state, right? Now we also talked about having a Markov option versus not semi-Markov options, and we also talked about how primitive actions can also be considered as options. Okay, now we can use this idea of options to learn the policy. Okay, so the first algorithm that we are going to see is SMDP Q-Learning. Okay, now, well, it's not a new algorithm, like it's same Q-Learning algorithm, just extended to SMDP setting. Like so, in the case of flat Q-Learning, like so you had Q of S comma A. We talked about Q of S comma A, right? Like so, now we are going to talk about Q of S comma O, where O is the option. Okay, now Q of S comma O is going to be Q of S comma O plus alpha times. Okay, now my R plus gamma power K max over A belonging to option Q of S dash comma A minus Q of S comma O. Okay, so well, I think I kind of switched some notations, like so I will write these notations out. So O is my option. Okay, and K is the number of time steps between S and S dash. Okay, so that is equivalent to the capital N that we discussed previously. Like so, this option takes K steps. Okay, so that is the K, and R is not just one step reward. So this R that you're seeing here is actually a cumulative discounted reward over this time period. Okay, so this R is the return of this temporally extended action, like it is a reward of the action, but this action took many time steps, so we sum them together to get the return. Okay, so this is the reward by end of cumulative reward by end of the option. Is that clear?
So the A can be another option or a primitive action?
Yes, A can be. So my capital O set, right? Like it has all my options as well as primitive actions. So if you have access to this set, then you can do Q-Learning like this. You will learn a policy which is going to have a mix of actions and primitive actions. Is that clear? Now, for example, like we can go back to the four-room world again. Now, in this case, well, let's just say there's a goal somewhere. Okay, I want to reach the goal. In this case, like I could have this capital O, which is a bunch of options. This includes the primitive options, north, south, east, west. Okay, and it also includes the abstract options like exit through north, exit through south, exit through east, exit through west. Okay, this is my option set. Now, let's say the agent is here. So one way to solve this task is by first taking an abstract action, exit through north. Okay. Then taking the abstract action, exit through west. Okay. Now my exit options doesn't are not useful to reach that goal, right? Like so. Now I can start using the primitive action. I will say west, 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 and I reach the goal. So I can learn this policy by using SMDP Q-Learning. Is that clear? Well, it's a simple algorithm. So, okay. Now, there are some. Can we do better? Okay, yeah.
So in this case, like your primitive actions and abstract actions are combined.
Yes.
So your first two actions you use abstract action. What is preventing you from using primitive actions there?
Yes. So you could use a primitive action before taking the leave room north option. You can do that.
Like,
Right?
I mean, it is like at least the same amount of learning that I will do without the abstract actions plus something more. So would am I not like increasing my computational time?
No. Now you are going to find your target faster here because, like, if you take a primitive action, it is taking you many steps, right? So, sorry, if you take an abstract action, it is taking you many steps. You will not. Well, one of the goal here is like to learn faster. So, like, you will not take a lot of time. You will learn faster. Like if you will learn faster if the options are given to you. But if you also have to discover these options, then that becomes a problem. Yeah.
So when you say like options, you think that the agent knows how to exit?
Oh no! When I say options are given, it just means that like let's say exit through north, right? So exit through north, I will give you the policy. Like wherever you are, you call exit through north. That policy will figure out the north exit by itself.
Okay, so you don't have to learn that option.
You don't have to learn the option like that. Like so, like that option is given. But of course, who is going to give that? Like so, we have to design that as well. Like so, that you can do in parallel way as you described. Like so, like if I tell you that these are the 4 possible macro options, now you can train maybe a neural network to learn using policy gradient for each of these options separately. Now you have 4 different neural networks, like each corresponding to 4 options. Now the higher level agent can just consider this entire neural network as one option. Like so, you call this option, you follow the policy. So we are assuming that we have the perfect policy for these option subtasks, right? Like so. Now, sometimes you might have imperfect policies. Sometimes you might be learning these policies simultaneously. So it is all possible. Okay. Now, there is one major limitation with SMDP Q-Learning. Okay, so the limitation is it learns only after finishing an option, right? So, in some sense, what is happening inside the option is completely hidden for this update flow, right? Like so, from state yes, let's say you take 10 steps to reach S dash. This update jumps from S to S dash. However, an interesting observation is within this option, there are 10 time steps. And in those 10 time steps, you are taking some primitive actions, right? And you are taking some primitive actions, you are taking some subsequences of primitive actions. Maybe some of these subsequences might be useful for other options, right? It would be ideal if I can also learn within the option, right? Like so, if I can learn within the option, then I can generalize to other options, like options that I haven't even executed yet. SMDP Q-Learning is like limited in the sense, like you will learn to update only one option. But if you have this ability to learn within the option, it is some sort of off-policy learning. Okay, like just like how off-policy learning learns about one policy while behaving using another policy. Like you could have one option as your behavioral policy, while you can be simultaneously learning for other options, which are all your target policies. Okay. Now, how can we do that? So there is actually a very elegant way of doing that. Okay, so it's called intra-option Q-Learning. Okay, now, so intra-option Q-Learning is an off-policy method. Okay, so we're just going to learn while executing the policy, like about not just that policy, but also about all other policies. Okay. Now to do that, we have to first define a modified Q function. Okay. So we're going to define a modified Q function. So Q of S comma O. Okay, which is my Q value for taking an action, right? Like so. Now this is with respect to some options set O. Okay. Now I'm going to modify the Q star with a new definition, okay, which is 1 minus beta of S times Q O star of S comma O plus beta of S times max over O dash belonging to O Q O star of S comma O dash. Okay. Now, what does this mean? What does this mean? At each state, okay, let's say I start taking an option, okay, at each state, yes, okay, we know that beta of S is a termination condition. Like so, like if beta of S is 1, then it is stopped, which means you are going to take another action or another option from there, right? So I can have this modified Q function, which will be used within the option. Okay, within the option, there is an uncertainty of whether I'm going to stop or not. So this is like learning what if I stopped here and took another option, right? Like so, if I have an option which is 10 time steps, I can learn in every time step by saying, okay, what if I stopped in the first time step and took some other option? How will my Q-Learning updates be? Now, what if I stopped in the second time step and took another option? Okay, so now you see that from this just one option, I'm trying to generate as many experiences as possible. Okay, so it's much more efficient in learning. So with 1 minus beta probability, I'm going to stay with my option. So my Q value is same as that I would get from this option. However, with beta probability, I might switch option, in which case my Q value from that state is going to be max over all possible options. Is that clear? Any questions? So now, instead of having these Q values starting from the beginning to end of the option, we have these Q values defined throughout the option, right? Like so now I can actually write my optimal Q star as summation over A belonging to the action set, okay, phi of S comma A, expected value of R plus gamma times modified. Is that clear? Any question? So now this particular equation, right? Like it is not waiting for the end of option. It is actually updating things just after one action within the option. Okay. Now using this, I can have a modified one-step TD update, like Q-Learning algorithm, for example. Like so Q of ST comma O is Q of ST comma O plus alpha times, okay, RT plus 1 plus gamma Q O star of ST plus 1 O minus Q of ST comma O. This is a one-step TD update. Like so, now you see the difference between this and SMDP Q-Learning update, right? Like in SMDP Q-Learning update, you had the reward that you get from the option plus gamma power n times the next Q value, right? Here you are doing it just for one step. So this is within the option, like so. You do one step and you update. Now you will apply this update for every possible option from that particular state. Like so, if let's say there are 4 out of 5 options which has initiation set enabled for that particular state, then you're going to update all those options. However, remember that you are executing only one option. If you're executing one option, but over the period of this option, maybe you update 5 to 10 options. Is that clear? Any question about intra-option Q-Learning? Any question in the chat? Okay, so now I told you that like we will not talk about learning these options, but we can maybe have a very brief discussion before we jump to the next algorithm. So these two versions like that I showed you, like so the SMDP Q-Learning and Intra-Option Q-Learning, right? Like so they both assume that you have already learned a set of options. Now, how can you do these things like when you don't have anything like learned? Like so you are starting from scratch, but you have an option. You have an option to learn or discover these options. Now, it is kind of similar to asking what are the good sub goals to achieve the higher level goal, right? So how would, like, I'm looking for some intuitive proposals on like how can we discover sub goals. So maybe if it makes it easier for our discussion, we can go back to the 4-room world. Okay, so now I don't give you any options. There are only primitive actions here. Okay, now how can you come up with your own options here?
You can train for a little bit.
Train?
Yeah, like flat.
Okay.
And like there are some states that you always do.
Okay.
And that would be intermediate.
Yeah, okay, that's a good heuristic. So you train your flat optimal agent, and maybe there are some states that you often visit. Okay, so you can also call these states some sort of bottleneck states. In fact, there is an algorithm which is doing exactly what you described. Okay, so it's a bottleneck state discovery algorithm, like so, which will detect bottleneck states because these are crucial states. Like you have to pass through them. So you could very well have an option to reach that state, right? Like so, for example, like what are the bottleneck states in this 4-room world? The doors, right? Like so you always have to go through this door, like whatever policy you're taking. So now you can have this discovery algorithm, like which will discover these bottleneck states, and every time it finds a bottleneck state, like now you can, in parallel, train a reinforcement learning agent to go to this bottleneck state, and that is your option. Okay. You had a question or?
No, I was going to say.
Okay. So any other heuristics?
Can we change the reward function?
How would you change the reward function?
So we can define sub goals. I mean, we can give rewards when it goes to the other room, so that it learns first to go to the other room and then tries to go to the
No, but you're just transferring the problem from finding sub goals to finding these rewards, right? Like, so how would you design these rewards? So those are the sub goals actually. So, like the thing is, like the moment you discover that, for example, this is a bottleneck, and you want to train an agent to go there, then you have to design some reward function. Like so, you are anyway doing the reward function design. like for these sub goals.
There are other ways.
Sorry,
There are other ways.
I'm asking if there are other ways.
Are there?
Well, there should be many ways, like, so because we don't have a solution for this yet. Okay, so I will let you guys think about it, like, so, but at least this is the most obvious way. It works when you're in grid worlds, right? Like, so, but when you're in really complex environments, like, I'm not sure if this is going to scale up that well. So some of the other simple ways include, like, for example, like getting some assistance, right? Like, so, like, imagine there is a human who once in a while tell you this is a good option, this is a good option. So you can take these input and learn a policy for that and integrate it to your library. So you can also grow this library over time and continuously adapt your policy based on this growing library. Yeah, you have a question or point?
I thought about like choosing random options and maybe see what works best.
Choosing what?
Like we let the model with some random options, but like you select randomly and you see what works best, something like that. Like in a genetic way.
Yeah, you can do such evolutionary things. Maybe another approach is, like, for example, let's say you have expert trajectories available. Okay, so which we are going to talk about in the next lecture. Like, so next week we will talk about like how to learn your policy from a data set. Like, so, like, instead of having this option of learning to interact, let's say you are learning in offline mode. Like, so, like which is often the case for very critical and like sensitive applications. Like, so for example, like when NASA sent a rover to Mars, like you cannot do reinforcement learning in Mars, right? Like, so you cannot let the robot interact. You have the risk of like damaging the robot. However, you can collect all the trajectories of the robot and try to learn a good policy based on that and use that policy. Like, the advantage is, like, you will learn a policy, you will verify the safety of the policy, like you will adapt the policy for safety conditions and then deploy it, right? Like, so how can we learn from data? Like, that's something that we will talk about next week. But that is another way. Like, so if you have the expert trajectories, then you can go through these trajectories to find like significant subsequences or like most frequent subsequences, like, or most rewarding subsequences, and treat them as options, right? So there are many ways to do this. Like, so we will not get into the details. But to discuss algorithms that really work, like, so we might need to extend these algorithms to like deep reinforcement learning setting. Yeah.
When designing rewards or goals, if we say we have to exit one grid, won't there be a loop? Like, okay, I exited this grid and then go back again to the same grid. It's an example like trash picking account. So you throw the same trash and you pick up this.
Oh, but well, you will have such reward design issues even in flat reinforcement learning, right? Like, so, like, but here I think, like, once you exit the room, like, your option ends, like, so, like, it terminates. Like, so then you have to pick a new option. So, well, you might pick a new option which gets you to the cycle, but then you will learn that it is not doing any help. So you will adapt your policy. So this is still trial and error. Okay, so now we are going to talk about, so that's all about option frameworks. Like, now we are going to talk about another framework for doing hierarchical reinforcement learning. Okay, so this is called MaxQ. So these are all developed around the same time. So this is by Dietrich 2000. Okay, so the main, I don't know if I have the example here. Yes, I have the example. So the main premise of MaxQ framework is like somebody has given us the task hierarchy. Okay. Now, in the case of options, like we did not assume the hierarchy really, like we just had a bunch of options. We did not care too much about what is happening inside the option, right? So now in the case of MaxQ algorithm, like we have a task hierarchy given to us, and our goal is to learn a policy based on the task hierarchy. Okay. So here is another classical example, like the four room problem. Okay. So this is called taxi problem. Okay, so the task is to pick up the customer from, this could be a grid world. Okay, so like this is just task hierarchy, like so it could be a grid world, like where you have a taxi. Okay, and let's say the customer is here and the destination is here. Okay, and your car might be here. Now the goal is to pick up the customer from his current location and drop him or her in the destination. Now you could have many customers, in which case you are going to do a lot of source destination mappings. Okay. Now, how can we decompose this problem? Like one way to decompose this problem is pick up as one operation, right? Like so, wherever the customer is, you go find pickup. The other like decomposed task could be navigation. Like so, like given the source and target, how do you navigate from source to target? And the third task could be like drop the customer and so on, right? Like so, now here is a bunch of tasks and their hierarchy. So the root is the problem that I want to solve. Okay. Now there are two subtasks. So get and put. Okay. Now get is about going and picking up the customer. Now this requires two subtasks again, a pickup subtask and also navigation to point T. Okay. Now you can see this navigate T is actually a parameterized subtask. It takes an argument. The argument is T, like where to go. So instead of learning one navigation for every point of the grid, I can have this parameterized policy. Okay. And similarly, put is going to have a drop off, and it also requires navigate. Okay. Now navigate has a bunch of primitive options like north, south, east, west. Is that clear? So like the task, is the task clear? Any questions about the task? Okay. Now this is also another, I think these two are the famous examples that you will see in a lot of hierarchical reinforcement learning papers. Like so, both the four-room world and the taxi problem. Okay. Now, the key feature of MaxQ algorithm is this notion of task decomposition. Okay. Now, given the structure, I can also decompose my value function. Okay, so based on the task decomposition, I can actually do value function decomposition, which means I can learn part of these value functions in parallel, and hence I learn faster. Is that clear? Now, this is actually an example of recursive optimal algorithm. Okay, so it's recursive optimal because once you decompose, like whatever is happening in this decomposed part, like is not affected by, like you're doing a perfect decomposition. Like so, like learning happens within these subtasks. Is that clear? Okay. Now, how do we do that? So to do that, like we should go back to our Q function. Like so, let us write our Q function and then see how to decompose it. Like so, now for each task, there are subtasks, right? Like now, let us just call. Previously, we had this Q pi of S comma A, right? Like so, where A could be an action or a macro action, right? Now, instead of that, like now we are going to add more information. Like now we have this notion of subtasks, right? So we're going to put an extra M here, where M is the subtask that I'm currently working on. Like if I go to this hierarchy, put is a subtask, drop off is a primitive action, navigate T is a subtask, get is a subtask. Okay, so Q pi of MSA is given by summation over all possible next states and the length of the option, okay, length of the subtask. Okay, T of M SA S dash N. Okay, I'm adding M here. Okay, or again M SA S dash N plus gamma power N Q pi of M S dash pi of S dash. Is that clear? Is that clear? Now, in this case, my abstract action A has invoked subtask M. Okay, it invokes subtask M, and if I follow this policy of subtask M, this is what my Q value is going to be. Is that clear? Now let's think about this whole Q value as like how to decompose it in two parts. Okay, there are two parts in this Q value. The first part is the value within the subtask, and the second part is whatever the rest of the value until the completion of the task. Right? So I take a subtask, maybe I'll take another subtask, I'll take another subtask, I'll take another subtask, and I finish the task. This is the end of the task. I reached the destination. Okay. Now, MaxQ decomposes this Q value in the sense I'm going to decompose my Q value as two parts. The Q value or the value for that particular subtask plus we are going to call this whole thing as completion function. Okay, now this is the value of completing subtask MA. The first part is the value for completing this subtask, and the second part is the rest of the value for completing the entire task. Is that clear? Now, if you think about this equation, right, like that, the equation that I have here, this second part is what is about the rest of the task, right? The second part is about the Q value after this subtask is over. Now I can actually decompose this. So we're going to give a name for that. So we're going to call C of MSA. Okay. Now the C function is what is the rest of the Q value after the completion of this task. So this is nothing but summation over S dash N, T of MSA S dash N, gamma power N, Q pi of M S dash pi of S dash. Is that clear? So now I can actually decompose my Q function. So Q pi of MSA is equal to V pi of MA comma S, which is the value for completing the subtask, plus C pi of MSA. Is that clear? Yeah.
Kind of confusing. So A is the subtask or M is which one is calling which one?
Okay. A is the abstract action, and this abstract action could call subtask M. So MA is that version. I know that the notations are a little bit confusing. Okay. Now I can do this recursively. So now what is the value of this subtask? That is going to be dependent on whether this action A is primitive action or abstract action. Okay. So if A is just taking primitive action, okay, then it is the estimate of the return, right? Like so V pi of MA comma S, okay, is going to be just an estimate of the return, summation over S dash T of SA S dash R of SA S dash, if A is primitive, okay. However, if A is abstract, then we have the recursion. So it's going to be Q pi of MA S pi of S if A is abstract. Okay. By this way, I can actually decompose the entire Q function, Q pi of M0 S pi of S as B pi of Mk of S plus C pi of Mk minus 1 S AK minus 1 plus C pi of M1 SA1 plus C pi of M0 SA0. Is that clear? Now, so what have I done here? So M0 is my root task, okay? So what does this mean? This means that if I give you the hierarchy, okay, so let's take any random hierarchy, something like this. If I give you a hierarchy, and what we really care about is the Q value for the root task, right? I can decompose the Q value of the root task by the corresponding completion values of the individual subtasks. Okay. Now, if I have to take an action at this level, then I need to do a max over all possible Q values, right? Now, taking this max means you have to do a depth, like you have to do a complete search over this tree. Like so, like what happens if I do this? You sum all these things, you compose back the Q value. Or what happens if I do this? 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 Right? So you can compose these Q values back and then pick the max action. Okay, so that is why this algorithm is called MaxQ. Okay, so the V star of MA comma S is given by max over A dash Q star of MA S A dash. Is that clear? So this is why it's called MaxQ. Now, the biggest advantage of this kind of decomposition is like I can actually in parallel learn all these things, right? I can have like an approximate update rule for a completion function for each of these tasks, and I can at any point of time, like if I have to execute a policy, I can put together all these things and do a search. Like I think the original MaxQ algorithm does a depth first search, but you can do any sort of search over this and then execute. Now there is also a bit of computational complexity involved here, because if the tree is too big, then like taking every action is like really difficult. So like it takes a lot of time. So normally this works with smaller trees. Like if you have a big tree, then you have to like come up with better heuristics. Well, then, for example, we know you can do some sort of smart modification to Monte Carlo tree search. But here you are not doing a tree search over actions. You are doing a tree search over subtask tree. Okay, so those things are possible. I think I have the algorithm. Okay, yeah, so we have the algorithm here, but this is really a old version of the algorithm, so it might not be, it might not resemble the algorithms that we have seen so far. But nevertheless, let us try to decode what is here. So at any point of time, whenever you are taking a primitive action, okay, you can learn the value function as usual. Okay, I think this algorithm is like doing simple Monte Carlo. Okay, so we are just doing a running average of the value function. So you can learn the value function. However, if it is a complex action, okay, then you do the MaxQ. You do the MaxQ, you move to the next state, okay, and you do the C function update for each of these subtasks that were involved. So once this algorithm converges, then you have an estimate of B functions and C functions. You can put these things together to do the final like policy. Is that clear? Any questions about MaxQ? Okay, so so apart from the lecture notes, I will also give link to a couple of references for today's lecture. Like, so one is a survey on hierarchical reinforcement learning, I think 2003, but the other one is a 2012 chapter on hierarchical reinforcement learning in another textbook. They both have more detailed explanations of these algorithms, but I will also give in the reading like the original Intra-Option Q-Learning paper and MaxQ learning paper, like if you want to learn more about these algorithms. Yeah, question?
What is that evaluate team doing? 197.
I don't know. I have to. So there are other parts of this algorithm which is not here. Well, their notation is really old. This is from a 2000 paper. My guess is you are observing the next state as dash, and then I think it is just the. I think it is just computing the value function or return for that particular subtask. Oh no, it is a return from the subtask. Oh, no, it is a return from the subtask. If you look at the next equation, okay, no, I know what it is. So it is the return from the end of the subtask. You finish the subtask, then what is the return from the end of the subtask, right? That is what your estimate for C functions. Okay. Well, roughly we are trying to learn both V functions and C function. Now, what is a V function? A V function is just a return for that particular thing. A C function, on the other hand, is after completing the subtask, what is the remaining return? So you can do a Monte Carlo estimate of that. So that is exactly what line 12 is doing. Okay, so any other questions? Any questions in the chat? Okay, well, so I think we can summarize, like, so now I can go back to our big organization of reinforcement learning algorithms, right? Like, so now to remind you, like, so there are like one possible split is whether it is model based or model free, right? Now, in the case of model free algorithms, we have methods like TD or Monte Carlo or end-step TD, right? And we also have reinforce, action critic. For model based, we have the DP methods where we assume that the model is given, or you can also learn the model. Like for learning the model, we looked at Dyna, right? This is one categorization. The other categorization is like whether you are learning the value function or you're learning the policy. So these methods, like they learn the value function, so they're value based, right? So reinforce is an example for policy based. Up here. And actual critic is in fact a combination of value plus policy. Right? So now today we discussed one more level of generalization. Like, so you could just consider all these things as flat oral algorithms, right? Now, which means you can actually develop hierarchical version of all these algorithms, like if you want. We saw some examples for Q-Learning, like, but you can take any of these algorithms and develop a hierarchical version by using the SMDP framework. Is that clear? So next week, I think we will talk about two important topics. Like, so, like one is like how to learn from offline data. But there's another thing that we completely avoided for the whole semester, but nobody asked me, which is the notion of like partial observability in problems. Okay. Now, all the problems we have seen so far, like we assume that we have access to the entire world, right? Like at least in the state representation, right? Like, so now for a real robot which is moving around this room, it has a limited perception. Like, so it can only see part of the room. So in that sense, like that robot is partially observable. When you are in a partially observable setting, the Markov assumption doesn't hold anymore, right? Like, so your current state is not enough to take the action. Like, because let's say I'm standing like this. Now I don't have the view of what is in the back. So I cannot take an action without integrating all the other sources of information, right? Like, so like we will develop another variant of MDP, which we are going to call as partially observable MDPs. Like, and we will talk about how to do learning with partially observable MDPs. And so these are the two things that we will cover next week. So I think we will stop here. I can take questions. And as usual, this is my office hour. So in case you want to talk about your project or anything, you can contact me.